also an example of elastic collision. Molecules in a gas, when they're colliding each other, there's also another example of elastic collision. So you can simulate them as elastic collisions. Now you're gonna hear me go between perfect elastic collisions and elastic collisions. The examples that we're gonna be talking about are perfect elastic collisions. And the perfect basically means that there's absolute no deformation of the object. You can have an elastic collision and have a little bit of deformation. If you bounce a ball on the ground, you can imagine that when the ball is bouncing, there's a little deformation of the ball. So that's a non-perfect elastic collision. But if you have a steel ball and then you jump on the floor, the ball is going to still bounce, but then the deformation is going to be almost zero. So you can assume that that's a perfect elastic deformation, perfect elastic collision. Make sense? Now, the math, the equations for the perfect elastic collisions are a little more complicated because now we have two equations to satisfy. We need to have conservation of momentum and we need to have conservation of energy. Both of them satisfy at the same time. So for conservation of momentum, I'm going to have this. So I'm going to have conservation of momentum. For conservation of energy, and specifically kinetic energy, I'm going to have 1/2 I'm going to have those two equations that I need to satisfy at the same time. Now, Mary, you want me to go through all the math?
I'm writing it down.
Okay. Sylvia, should I go through all the math?
It's up to you if you want to.
Say no. It's too long. So what I want to do is to find an expression for the final velocity of the first mass. So I want to find an expression for the final velocity of the two masses that satisfy those two equations. So it's an insane amount of math, an insane amount of algebra. It's not terrible difficult, but it's just long. So I'm gonna, and usually when I do it, the students fall asleep and then they completely go to the happy place and then completely ignore and then just come back when I get the final equation. So I'm just gonna skip all that painful stages and I'm just gonna write down the final equations. But if anyone wants to see the derivation of the equations, I will be more than happy to do it in an office hours. Okay? So these equations are not in your book. Okay? So make sure that you write it down and that you write it down correctly. Okay? So for the final velocity of the first mass, we're going to have this m1 minus m2 over m1 plus m2 times the initial velocity of 1 plus 2 times m2 b to I, and the final velocity of 2 will be 2m1 Okay, I'll give you a couple of minutes for you to write down the equation. Make sure that you have the subindices correctly. Alex, give me a couple of minutes, and when everybody's done copying the equation, I will bring down the page. Yeah, everybody got it? Okay, I can return it back. Alex, is that okay? Okay, so I'll show you the equation again in a minute. So the equation that is in your book, it assumes that you're gonna have one of the masses is always gonna be static, that the initial position of the second mass is gonna be static. So when you assume that consideration, questions get simplified a lot. So I'm gonna show you a more general case in which what happens when the two objects are moving and what happens when you have a collision, because I think that's a little more interesting, and it doesn't necessarily make the questions more complicated or a lot. However, there are a couple of simplifications that we're going to assume. One of them is that the collisions are always going to happen in a single axis. It's always going to happen in a single dimension. So we're not going to have collisions in X and Y directions. It's always going to be in the X direction. Okay. So what I'm going to do is I'm going to assume that we're going to have the collision of two objects, and that the second object is going to be the initial velocity of 2 is going to be 0. So if the initial velocity of 2 is 0, then these two terms are going to cancel, and they're going to be 0 too. Okay, and then we can see a little bit of what is the meaning of these equations. So we have mass 1 and we have mass 2, and I have a velocity of 1 different than 0, and I have an initial velocity of 2 equals to 0. Then, and we assume that this is a perfect elastic collision, then the equations for the final velocity of 1 is going to be m1 minus m2 plus m2. No, this is, yeah. Final, initial. Okay, I'm going to have that. Okay, so imagine that you have two objects that have the same mass. So if the two objects have the same mass, then look at what happened to the velocity of the first ball. So if the two masses are the same, then you're going to have m1 minus m2, then this is going to be 0. And then that means that all this is going to be 0. So the final velocity of 1 is going to be 0. So if this equals to, if the two masses are the same, then the final velocity of 1 is going to be 0. Now, for the velocity of 2, well, you have 2 times m1. The two masses are going to be the same. So we're going to say m1 plus, it's going to be twice this mass. So all these factors are going to be 1. And then you're going to have that the final velocity of 2 is going to be equal to the initial velocity of 1. Yeah? Have you guys played billiards? Pool? So have you ever done that shot that you have your cue ball, you have your target ball, and then if you hit the cue ball perfectly in the center and you hit exactly the other ball at the center, your ball comes to a full stop and the other one comes going the other way? Well, that's basically what's happening here. You have two masses exactly the same. The first one, the one that is moving originally, comes to a full stop, and then all the momentum, all that energy is going to transfer to the second one. So that's what this equation means. Okay. Now, imagine that we have another case in which the first mass is bigger than the second one. That could be the example of a bowling ball hitting some pins, something like that. So if you have this case, then N1 minus M2, then the numerator is going to be positive. This denominator is always going to be positive no matter what. And basically where it's going to end up is that the final velocity of one is going to be on the same direction as the final velocity of the initial velocity. So the final velocity has same direction as the initial velocity. Probably it's going to be a little bit less, but it's going to continue going forward. So it's not going to stop. It's going to continue going forward, probably at a lower velocity. And if M1 is less than M2, so you're hitting a small object, hitting a larger object. So imagine a tennis ball hitting a bowling ball. So if you have that case, then this numerator is going to be negative. So that means that the final velocity on one is bouncing back. So whatever direction B1 has, B final is going to have a negative direction to that one. So it's going to bounce back. Okay. Yes, sir. There you go. Yeah, makes sense. Okay, so let's do a very quick problem. And I'm going to assume that I have a mass of 10 grams, and it has a velocity, sorry, it has an initial velocity of 20 meters per second. And it's going to hit another object, and this object is going to be 1 kilogram. And the initial velocity is going to be 0. Okay, so really quick, just calculate what would be the final velocity of the first mass and what would be the final velocity of the second mass. You are missing some. Oh, this should be 19.6. Okay, so I'm gonna do it real quick. So we have the velocity of 2, the initial velocity of the second mass is going to be 0. So the equations are going to simplify. So for the final velocity of 1, I'm going to have m1 minus m2, m1 plus m2 times the initial velocity of 1. So this will be 0.01, that's going to be the 10 grams, plus minus the 1 kilogram over 1.01. I'm just adding the two masses times 20, and I think this one gives you negative 19.66 meters per second. Okay. Now for the second mass, this is going to be 2 times m1 over m1 plus m2 times the initial velocity of 1. So that would be 2 times 0.01 over 1.01 times 20. And you get, Mary, what you got?
0.396.
396 meters per second. Yeah? Everybody got that? Magina, you were able to find out the...
Yeah, I put it in my head really well.
Okay, makes sense? That's pretty straightforward. Now, when you add the second mass, when the second mass starts moving, they try to figure out what is the final result of the equation. It's a little more complicated. And if you have more than one object, well, then it's pretty much impossible to figure out just by looking at the equation. So we'll do the same problem, just a little bit different, just to see how the initial conditions can change the final velocity. So I'm going to assume that I have two cars. And I'm going to have the car 1 going to have a mass of 1,000 kilograms. And it's going to have an initial velocity of 30 meters per second. Mass 2 is going to be 500 kilograms. It's a smaller car. And it has an initial velocity of 40 meters per second. However, they are going to face each other. So I'm going to say that the second velocity is going to be negative 40 meters per second. So you can imagine that this car is going to go like this, and the second car is going to go like that. Okay, so again, I want to find out what is the final velocity of the first car and what is the final velocity of the second car. Now, when you do this problem, just be careful. The sign of the velocity matters. Okay, so that's going to change your equations. This one. And you got it? Okay, I'll give you a couple more minutes for everybody to finish. How many of you are gonna take biomechanics next semester?
Part of this,
No, it's IPH 345. No? Is anyone on the chat, if you guys are gonna take biomechanics, just raise your hand. Okay. How many of you are gonna be taking Physics 113? Sarah, you're not? Why? But it's not about having to. Oh, only 8 people? Oh. Okay. So I'm gonna solve this one a little bit. Well, we're gonna go through this problem. Okay. So now the two objects are gonna be moving. So we need to look into the general equation for elastic collision. So for the final velocity of one, we're gonna have m1 minus m2. This is the long one. V1 initial plus 2m2. No, 2m1. What did I have? 2m2? M1 plus M2, B2 initial. Okay, so I'm just gonna substitute values over here. I'm gonna have 1,000 minus 500 over 1,500 times 30 plus 2 times 500 over 1,500. And here, when you have the velocity of the second mass, because it's going in the opposite direction, you actually need to put negative 40 meters per second. Okay, so you have to be careful with this. Remember, velocities are vectors, so there's actually a difference whether we have a positive or negative vector or whatever. Even though we're just working with one axis, the negative or positive just tells us if it's going to the left or to the right. That's all it means. And here, Sylvia, what you got?
As the total, negative 16.67.
Now 1667 meters per second. So that means that the first car hits the second one and it goes back on the opposite direction. Okay. For the second car, we're gonna have 2m1, m1, m2, b1 initial plus m2 minus m1, b2 initial. Okay. And here we'll have 2m1, that will be 2 times 1,000 over 1,500 times 30 plus 500 minus 1,000 over 1,500, and again times minus 40. And here, Mary, what you got?
80 meters per second.
80 meters per second?
Yeah, I don't know if that's right.
No, it's a little bit too high. Sarah? Emma?
53.3.
53.3 meters per second. Okay. Now, the original velocity of this car was -4. So this means that it was going this way, it crashed, and then it's going back in the opposite direction at a higher velocity. Okay. Now, what is the change in momentum of the first car? Actually, you can calculate the change in momentum of both cars. Yes.
For the final velocity of the second one, I got 26.7.
Anyone else got that?
I had that, but I did my math, and I made a mistake when I did the 500 minus 1,000.
This should be negative.
Okay.
So you got negative times negative.
Okay.
Wait, like the first division?
You got a question?
No, not yet.
Okay.
No, I can't write that one.
I am now. I have this, but that was what you did here, right? I don't know what to do with it.
So you're just looking at the change momentum of one object.
Okay.
So you just look at the final and initial velocity of mass number one, and you calculate the change momentum, and that would be delta V.
Okay.
Okay. Yeah. So you're not solving; you're just calculating a specific function. So you're gonna have.
I'm gonna find one. Not the one I had written down.
So you already have all of it. So you're gonna end up with a delta V equals blah blah blah. Okay, so you're not really solving for a specific fact. No, I don't.
Are you all flustered?
Yeah.
Ooh, that. Mary, I think delta P equals, mass, velocity final minus epsilon.
So remember delta P, the definition of delta P is just basically, it's a change in momentum. So it's the final minus initial momentum. So it will be M B final minus M B initial. So we are looking at the change in momentum of a specific mass. So when you are talking delta P1, it will be the change in momentum of that mass. Okay. Emma, you got both of them? Can you got both of them?
So,
Okay.
maybe.
So you can see it's almost the same.
Mhm.
Probably they're not exactly the same because we are changing these numbers. If you add all the momentum, it's going to be equal to 0.
Okay.
Okay, so on this one, on the first one, we're going to end up with a negative number. And can I, what you got? 46,000?
Yeah, 46670.
670 Newton seconds. And Mary, what you got on the second one?
46650.
50 Newton second. Okay, so we know that this equation, this collision has to satisfy that the change in momentum is going to be equal to 0. So whatever momentum we have at the beginning has to be equal to the momentum at the end, or that whatever change in momentum we have on the first mass has to be equal to the change in momentum of the second mass, just in opposite direction. So we can see that the two change in momentums are pretty much the same. There's a difference of 20 Newton seconds, but that's probably is because we are truncating these results. We're not using the whole decimal, so that's basically that 20 Newton second. But basically, if you add the change in momentum in 1 plus the change in momentum in 2, that's going to be equal to 0. Okay, so we indeed have conservation of momentum. Now, what will be the impulse on the first mass? Anyone in the chat or in person, what will be the impulse of the first mass? Mary?
I don't even know what impulse is right now.
We just saw it last week, but I'm done.
That's a long time ago.
Emma? It is the same thing. Impulse is the change in momentum. So the way we talk about impulse is that Ft equals delta P, and we call this the impulse. Okay, so if you calculate delta P and you calculate delta P to be minus 46,000 Newton second, the impulse of that mass is going to be equal to the same, negative 46,000, blah, blah, blah. Okay, if I give you the time of the collision, how long it took for this collision to occur, you can calculate what is the average force experienced by the drivers. Okay, makes sense? Okay, any questions so far? Okay, so the next couple of days, we pretty much are done with the with this chapter. So what I'm gonna do for the rest of the week is just gonna go through a couple of problems. I'm gonna give you problems and we're gonna try to do them together. I'm gonna show you a couple of old exams so you can be a little bit prepared for the exam next week. And next Monday, we're gonna start with fluids, which is something, a new topic completely, okay? So there's only 2 more topics that we're gonna cover during the semester. One is fluids, another one is kinematic equations. So fluids is chapter 12 or 13, and kinematics equation is chapter 1. So we're just gonna go and jump all over the book again. But that's pretty much it. That's all that we're gonna cover this semester. I'm kind of surprised. I never get to teach fluids, so yay! I'm excited about that. So have a good day. See you on Wednesday. Yes, Elisa. Elisa, you can just speak up. Thank you, Elizabeth.